morning, everybody. I'm going to start by apologizing for talking to you in English. I come here to Romania and I don't speak any Romanian. I'm very sorry. So I want to talk about software engineering this morning. And I mean that kind of in the broadest sense. I'm going to explain what I mean. But to give you a little bit of background, I spent the early part of my career doing jobs called things like a junior software engineer or a senior software engineer. And during that period of my career, I did no engineering at all. Nothing that you could think of as engineering. A bit later on, I started working for some trendy companies, and we thought that engineering was the wrong thing to think about, and we didn't like calling ourselves engineers, so we called ourselves things like software developers or just developers and all those sorts of things. And we still weren't doing any engineering during that period of time either. And then a little bit later, I had the good fortune to work on some projects which were really very difficult. And in order to make progress, we had to do some engineering. And I learned some lessons. And so I'd like to talk a little bit about that, about how it impacts on the way in which we think about software development as a practice. Good. Right, whoops, sorry, too far. So here's a picture. When I started talking about software engineering, if any of you have done any thinking about software engineering at all, you're probably thinking about something like this. This is to software engineering what a soldering iron is to electrical engineering. It's a tool, it's interesting, it might even be useful, but it's certainly not engineering. It's just a picture. So this isn't what we're really talking about here. You might think about other things. You might think about development process. We're here at the Agile Mammoths Games as we're thinking about agile processes and so on. This is probably the most successful agile process. This is Scrum, and it's a useful process. Any ideas how many times the documentation for Scrum mentions the word code or software? Thank you. Somebody at the back. 0. It mentions them 0 times. It's a useful process. It's useful in terms of project management. It's useful in thinking of organizing things. But it's as true of plumbing as it is of software development. So this isn't software engineering because this doesn't say anything about software. In recent years, it's become popular to talk about software development in terms of craftsmanship. And I think that there are some good reasons for that, which I'm going to go into later on. But this too is not engineering. Craftsmanship is a different thing to engineering. If we start to think about the history of production, the history of producing anything through humanity, I think it goes through these 3 stages. Essentially, through the vast majority of history, everything that we as human beings created was through a process of craft-based production. And that allowed us to do some things, but it wasn't until we started applying some more disciplined approaches that things like the Industrial Revolution and the modern information age and all those sorts of things become possible. So mass production came along and started to change the way in which we could think about production. It came along about the middle of the 19th century and started introducing techniques that allowed us to scale up and go faster. And then at the end of the Second World War, Deming went to, a chap called Edwards Deming went to Japan and introduced them to the ideas of more scientific rigor in terms of process and production engineering, and gave birth to the movement that led to lean production and lean thinking. And lean production techniques are probably the dominant factor in most industrial scale production these days because they work so much better than any other form that we know of. So let's look at each of those in a little bit more detail. Craft-based production is really an art rather than science. It's down to the skills of the individual craftsperson that's doing the work. There are no work standards. It's just down to the skills and experience of the person. Each piece of work is individually handcrafted. The commitment of the individual is going into it, and it's based on that individual's expertise. I think it's fair to say that in general, we tend to have a fairly romantic view of craft-based production techniques. We like the idea of craft-based production. If we're very wealthy, we buy our cars with hand-stitched leather seats because that's a sign of class that you've had your seats hand-stitched. But in reality, craft-based production is lower quality. For a moment, just consider a handmade one of these. It's a ridiculous idea. Even the prototype of an iPhone was the outcome of an industrialized engineering practice. You can't prototype even something as sophisticated as this with just craftsmanship. So we moved on and we started thinking about other approaches. Mass production came along. The first mass production was actually in horrible context. The first mass production was the mass production of weapons during the American Civil War. And there's an interesting story about the man who won the contract to supply the northern states in America with their rifles. He went to Congress with a sack full of components of rifles, and he poured the sack out onto the floor, and he asked the congressman to select different pieces of rifle from the pile, and from those pieces, he built a rifle. That was the first time in history when you could do that, because prior to that, there was no standardization. Any rifle that you bought prior to that was hand-built from scratch by a craftsperson. And you probably got a mold for your bullets at the same time, because your bullets would have been unique. They'd have been different to everybody else's bullets. So it didn't scale. So one of the horrors about the American Civil War, it was the first industrialized war, and it kind of took advantage of the economies of scale that mass production can give you, and so it killed lots of people. But mass production is about assembly lines, standardized components, the standardization of steps. We kind of pigeonhole each act as we move through. It's about piece-based metrics. We measure the rate of progress of our process by counting how many components we have built so far. And that was kind of the production mechanism through the first half of the 20th century, well, and probably the latter half of the 20th century. It's been overtaken a little bit now, but it's a very effective practice. It definitely scales up more effectively than craft-based production techniques. And then lean came along, and lean is a different kind of thing. It kind of takes a little bit of each of the others. It's about quality at source. It's about focusing on high-quality outputs, as a master craftsperson would. In the same way, we want to kind of focus on doing sort of wonderful pieces of work. It's a pull-based system. If you think about mass production, you're building all of these components. You're kind of pushing all of the components down the line towards a finished thing. Lean is the other way around. You have just-in-time delivery. You get the components built just in time for you to use them, and you take them. You have just-in-time manufacturing, just-in-time resource supply, all of these sorts of things. And it works in the opposite way around. Lean talks a lot about minimizing the amount of work in process so that we can kind of move very quickly and lightly. Minimizing waste through that process. And it introduces ideas like one-piece flow. We build one thing through to completion before moving on to the next thing. Another interesting way to kind of think about this is to think about the processes themselves as an academic thing. And one of the disciplines that's very good at processes in general is the chemical engineering profession, because their job is to industrialize different kinds of processes to produce different chemical artifacts. And so they have a taxonomy for identifying and describing different sorts of processes. Here's one description from one such process control model. So, defined process control model requires that every piece of work be completely understood. Given a well-defined set of inputs, the same outputs are generated every time. A defined process can be started and allowed to run to completion with the same results every time. This is the kind of space where mass production plays, assembly lines play, and waterfall processes play. Unfortunately, this looks nothing like any software project that you've ever seen in your life. Software projects don't start out with giving the same set of inputs, producing the same set of outputs. It's not controlled in every way all of the time. They just don't work like that. So the chemical engineers have another process control model. They have multiple ones, but this is the other one that's interesting in this context. And that's called the empirical process control model. So the empirical model of process control provides an exercise of control through frequent inspection and adaptation for processes that are imperfectly defined and generate unpredictable or unrepeatable outputs. I think that sounds quite a lot more like the process of software development to me. And therefore, the things that would play well in this kind of space would probably play well in our space. Those are craft-based production techniques. Exploration, continual improvement, and lean process. They work fundamentally in this kind of space. There's a reason why waterfall development doesn't work very well. It's the wrong model. It doesn't fit our problem space. So if we start applying these more empirical discovery kind of approaches to developments, we find that we get some good impacts. I think one of the reasons why the idea of software craftsmanship gained some ground during the early part of this century is because it was in reaction to the big high ceremony processes that were going on around the world in software development based on waterfall processes. We were doing this kind of high, big, complicated looking engineering approach which didn't really work, and so in reaction people started going down the road of craftsmanship. And that makes sense in the context of this model, because craftsmanship is a reasonable fit for these kinds of exploratory kinds of bits of work. Unfortunately, as we've discussed, it produces lower quality output. So is there a way in which we could kind of gain the benefits of getting more repeatably, reliably higher quality output and the kind of the ingenuity and the discovery that is inherent in craftsmanship? So where are we now? I think we are nowhere near mass production, and I don't think we ever will be, because it's the wrong model. It doesn't fit our problem space. If we were to create a mass production industry, we'd be doing it wrong. So I don't think we're there. I think we are here. I think we are a craft-based industry. One of the hallmarks of a craft-based industry is that the standards are variable, and if you look at the productivity and the quality and effectiveness of what we think of as the high-flying software development teams compared to the average, there's a marked difference. And so we see the hallmarks that we are a craft-based industry. If you think about the nature of software development in your organizations where you work, it's probably about people making guesses and thinking about things and just working on that basis. And I think there are some better ways which we're going to explore. I think that where we should be aiming is here. We should be starting to apply in-depth, more lean kind of thinking to the way in which we work. And I think that when we do that, we see some kind of remarkable outcomes. One of the things to kind of reinforce this point of the model for software engineering is to think about what software projects should look like. And if software projects were normal things, there would be a normal distribution of software project success, as many software projects would finish ahead of schedule, under budget, delighting their users, as finish behind schedule, over budget, and annoying their users. But I don't think that's what we recognize as normal for our industry. I think that mostly our industry is kind of based on a curve that looks more like this. And we kind of start off assuming that things are going to go badly. We're going to start off assuming that we're going to be late. We're going to start off assuming that there's going to be lots of bugs in production. And so we'll buy a big bug tracking tool because we're going to need one of those, right? And all those sorts of things, we just start off as assumptions. They're not inevitable. It's not a natural consequence of software development that you have to have those kinds of things, has been my recent experience. When we get it right, we see quite astounding changes. And that's not surprising. If I'm right, if we've got the wrong model and we start applying the correct model, we'd expect to see a big impact. All of this is based on largely peer-reviewed data from research into our industry using strong statistical sociological techniques to look at how our industry works. You see orders of magnitude reduction in defects rates. You see dramatic improvements in productivity across the board. Bottom line, organizations that practice these kind of more disciplined, iterative, incremental approaches make more money than organizations that don't. These are quite staggering ideas, really, and we haven't had this kind of data before in our industry. So I'm talking about engineering, and I don't know how many people in the room consider themselves at the technical end of software development or software engineering, but when I start talking about engineering, well, nearly everybody ends up, for some reason, talking to me about bridges. They come and say, yeah, but Dave, it's not bridge building. And no, it's not bridge building. But mostly, our idea of what bridge building is isn't bridge building either. If you're building the first version of a bridge that's ever been invented, the first time that you built a bridge like this, My bet is that the people that did this did lots of research, lots of experiments. They probably built models. They probably put them in wind tunnels. They did all sorts of clever things to figure out how to do this. One of the mistakes that we make when we start talking about engineering very often, we software developers, is that we start thinking of engineering in terms of production. And that's the boring part. Production isn't our problem. When we press a button that runs our compiler, that's production for us. That's easy, or it should be. But the interesting part for us is the design. It's the exploration of the problem. It's understanding the problem sufficiently that we can create a software solution that fulfills the needs of the people in that problem space. That's our job. It's the design problem. And engineers have got that nailed too. If you're designing a spaceship, it's going to be a research project. You're going to be exploring. It's not the same thing as production. So I want to try and banish from your mind any ideas of production. We're not talking about bridge building in the sense of delivering the bits of steel and the concrete. That's just logistics. That's a different problem. We're talking about design. We're talking about the exploration of things using technical thinking. And then again, when we start thinking about engineering, all engineering is not the same. Even outside of software engineering, house building is not the same as building bridges. Aerospace engineering is different. Electrical engineering is different. Chemical engineering is different. Each of these disciplines is different. It's unique. And so one thing that we can tell from that is that anything that we invented that fulfill our needs, that solve problems in our space, that we could honestly call software engineering, is going to be different. It's going to be ours. It's going to have some unique properties that are special to us. The other way in which engineering is not the same is a matter of scale. And this is kind of slippery for us. It's because software is by nature soft and ephemeral, it's sometimes hard to tell the differences. I show you these two pictures. These are both engineered structures. The structure on the left was engineered. You can bet if that was an IKEA shed, it was kind of engineered to the last cent to make sure it was within a price point. The building on the right is the Burj Khalifa building, which is the tallest building in the world. That was stretching the boundaries of what's possible. When they were building that, you can bet they were using every resource at their disposal. They were doing clever maths, doing finite element analysis. They were building models. They were putting them in wind tunnels. They were shaking them as though there was an earthquake. Everything. Well, that's what they would have been doing to build something on that scale. That's what engineering is like in that context. For us, looking at those pictures, it's absolutely crystal clear that the engineering for the building on the right was at a different scale to the engineering on the building on the left. If, on the other hand, I'm writing software, I don't know, for medical scanners that people's lives depend upon, and for my mum's cake shop, it's not necessarily obvious that the level of engineering that goes into those is different. Because on the surface, they probably both got a web front end, and they probably look vaguely similar in some ways to the unprofessional eye. And so we need to think about that as well. So the level of engineering that goes into our development process, it probably depends on the nature of the problem that we're going to do. And if we're building stuff where people's lives depend on the outcomes or fortunes depend on the outcomes, we probably want to invest a different level of engineering than if I was doing it from my mum's cake shop, where the primary loss would be my supply of cakes. So what is engineering? And actually, I'm going to start with what isn't engineering. I've been talking about this topic kind of peripherally for a couple of 3 years now. And from time to time, I get involved in conversations. And I was involved in this conversation with somebody on Twitter, and I've hidden their name because I strongly disagree with what they're saying here, and so I don't want to embarrass them by calling them out. But they said, for me, engineering means working in a certified inflexible process that includes planning ahead a lot, the antithesis of agile. I think that's utter nonsense. That's mistaking engineering for production. If you're designing something sophisticated using engineering principles, it's not a certified inflexible process. It's an exercise in creativity and discovery and experimentation. And that's what I'm talking about. So that's not engineering. So let's look at some, I did a version of this talk in Australia last year, and I got this tweet. So engineering is mostly about construction and automation and tools and processes around it. And I think that's absolute nonsense. And in talking about this, I was referring to the work of the Curiosity rover team, the people that built the lander that landed on Mars, that's still driving around taking pictures of craters and so on. And so I replied, no, it isn't. Was the design of the Curiosity rover mostly construction and automation? No, but it is engineering. And to my delight, I got this reply from Anita Sengupta, who is one of the engineers on the Curiosity rover project. She built the supersonic parachute system that opened in Mars's atmosphere to slow the descent of the vehicle. Just saying thank you. She agreed what we're talking about here is a creative discipline. We're not just talking about production. So I know I'm reinforcing that point, but it's worth considering because I have that conversation over and over again. So let's think a little bit about what engineering is. So here's the definition from Wikipedia, and there are some words that I'm not going to read through all of this, but it's about empirical evidence and scientific practical knowledge allowing us to design things. Here's another version. The art or science of making practical application of knowledge of pure sciences, blah-de-blah-de-blah-de-blah. And yet another one. The scientific mathematical principles to practical ends. So there are some words that are cropping up commonly in the definitions that we find of engineering. I wasn't quite happy with any of those definitions of engineering in my context, so I kind of came up with my own. So in this context, what I'm talking about when I mean engineering is this. It's the application of an empirical scientific approach to finding the efficient solution to practical problems. I think that's a reasonably good summary of what we're talking about when we're talking about engineering. All of those things are important. The empirical part, the scientific approach part is important, but the practicality is important as well. We need to think about the economics of the things that we build and how easy they are to live with. That's important in engineering as well. I think, let's start getting on now to what I really mean. And I think that any form of discipline that we could seriously consider as a candidate for an engineering discipline in our field would have to embody these properties. It would have to be grounded in these properties for me to take it seriously. So first, it needs to be iterative. Then it employs feedback. We're going to learn and we're going to adapt based on what we observe. It's incremental. We're going to build up systems piece by piece. It's experimental. We're going to be trying ideas out and understanding the impact of our ideas on our user community and learning from those and again adapting. And it's empirical. We're going to be doing this in real life. We're going to be measuring real outcomes, not just theorizing about them. Maths is not enough. One of the things that I think is a good thing and a bad thing for our profession is that software development appeals to the same kinds of minds, I think, that mathematics does. So I think that we, as a group, we tend to like mathematics more than the general population. As a result of that, we think in terms of maths. And maths is wonderful, and yet it's not enough. If you go and design an aeroplane, these days you will do lots of maths. You will do all sorts of clever fluid flow dynamic things and that. But you'll still build a prototype of the aeroplane, and the first time it flies, it's not going to have a full load of passengers on it. You're going to try it out first. You're going to see whether your maths was correct, because it might be wrong, because doing it right is hard. And so you need to be discovering this in reality as well. So let's go through each of those in a little bit more detail and kind of understand what they mean for us to practice as something that we might consider to be engineering. So first, iterative. Iteration is the act of repeating a process. The first bit's not interesting. With the aim of approaching a desired goal, target, or result. We want to home in on some desirable outcome. We want to iterate in order to be able to focus in and steer towards that outcome. Being iterative is really important because it means that we can learn, react, and adapt to what we find. I quite like the adapt picture there. There's people in a flooded room watching TV. It allows us to steer towards a goal. We can keep changing course. We perceive where we're going and we understand where we're going, and we keep changing course to keep on track. If you're going to drive from here to Bucharest, you don't take a bearing and say, okay, I'm going to, it's going to take me 5 hours or whatever it is to drive that in that direction, and I'm just going to do that and just drive. That's not how it works. You're going to drive a bit, and then you're going to see what's going on, and you look at the road conditions and the weather and all sorts. And then you might change your plan. You might stop for a cup of coffee, or all sorts of things might change the way in which you think about it. That's how you make more efficient progress. It's fundamental to a process of continual improvement, and that's again how we get better and better at things. Lean practitioners focus on continual improvement to a significant degree, and what they're trying to do is that they're trying to give themselves as many opportunities to learn as they can. And being iterative is one of the mechanisms that gives us more opportunities to learn, and therefore adapt, and therefore better target our outcomes. It also, because we're doing the same sorts of things over and over again, it allows us to practice and repeat and get better and better and better at the things that we're doing. One of the hallmarks of a genuinely high-performing agile team is that, in contrast to more traditional development teams, instead of the pace slowing and getting worse and worse and worse, the high-performing teams tend to accelerate. They tend to get better and better and better. And I've seen that multiple times through my recent career, where teams just go faster and faster because the longer they go, the more that they automate things, the higher quality their work is, the better their design, the easier it is to work with, and so they just accelerate over time. Feedback. So feedback is the idea of information about actions being reported back to the source of the actions. It gives us, again, this opportunity to understand what's going on and to react to what's going on. We can observe the impact of our choices. I tend to use this model for my favorite, what I think of as an engineering discipline, continuous delivery, and it's all about feedback. It's at the outside, it's about having an idea, getting that idea into the hands of our users and figuring out what they make of it. At the inside, it's about test-driven development and writing tests and seeing how our code works, and in between there are other forms of testing and so on to give us feedback. It's all about trying to learn, understand whether our stuff is really what we think doing, really doing what we think it is or what it should be doing. We want to be incremental. Evolutionary design, continuous design, evolutive design, or incremental design is directly related to any modular design application which components can be freely substituted. My wife calls me a serial nerd, and she's wrong because I'm a parallel nerd, because I can be a nerd on multiple fronts at the same time. So I'm going to parallelize my nerdism and talk about one of my other interests, which is aviation and space. And I'm interested in space exploration and was a little boy when the Apollo program was in place. And so this is the Saturn V. This is so far the most powerful rocket that human beings have ever built. Elon Musk is busy trying to build one that's going to be more powerful than this, but he hasn't done it yet. And this was an example of incrementalism in design. So one of the insights that the NASA engineers had was to build a modular system. This wasn't their original viewpoint, because when they first had the idea of going to the moon, they kind of imagined, has anybody seen Wallace and Gromit? The kids, no. So it's a kid's cartoon version of going to the moon. You have a space rocket and you fly it to the moon, and you land that rocket on the moon, and then you take it off from the moon and you fly it back to Earth. That was their model. It's in energy terms, it's a really inefficient model, so they came up with a modular system. So here's the first module that's of interest. That part of the spaceship is about getting everything else from Earth into Earth orbit. That's a difficult part, as you can tell by the proportions of the mass of the spaceship. The vast majority of the mass of the spaceship was just about that first 100 miles. And then the rest of the system was modular too. So this is the thing called the service module and the command module. The command module, this was the bit that was from Earth orbit back to Earth when the astronauts came home. And this bit is from the Earth to the moon, and from the moon back to the Earth. And then there was the lunar lander. So this was the spaceship that actually landed on the moon. And the first bit, that's from the moon back to lunar orbit. And the bottom bit is to take the astronauts from lunar orbit to land on the moon. If they hadn't had this idea, it wasn't possible. You couldn't solve the problem. The modularity of this system was a key aspect of it. It also gives you an interesting behavior because it's composable. A modular architecture, a modular system is composable. You can organize it in different ways. And they took advantage of that in multiple points through the planned mission. And when things went wrong, they were able to improvise and use bits of the spaceship as a lifeboat when the Apollo 13, when part of the spaceship blew up. So it's a more robust approach to design. So that's important as well. It has a knock-on effect in terms of the quality of the things that we can produce. And that's about the batch size, the size of the units of work. So we could make the decision to release change into production in large chunks. That's what most organizations do. Most organizations in the world of software development release on a frequency that's probably 6 months or longer. And so every 6 months, they're going to make a huge, large, bulky group of changes, and they're going to dump those into production. Or we could change our mind. We could instead release change into production in smaller pieces and more frequently. And that has a significant impact on the riskiness of our work. So I'm going to give you some math. It's kind of bullshit math. It's not strictly accurate, but it's a rough approximation of what I mean. The total risk of releasing change into the hands of users could be kind of characterized by a formula that looks vaguely like this. So we're going to have a part of the risk based on how many changes are going into production. If you're releasing software once every 6 months, you're not releasing one change into production every 6 months. You're going to be probably releasing hundreds of changes into production. So the first part of our risk calculation is how many changes you're releasing into production. The more changes you're releasing, the bigger the risk. That seems fairly obvious. There's going to be a little bundle of risk associated with each change that we make. And so the total risk is going to be the sum of all of those little risks. But there's another part to this formula. And so if we're going to be releasing multiple changes into production, there's the opportunity for one change to interact adversely with another change and screw things up. And now we've got a different kind of part of the formula. It's going to be exponential. This is going to be a function of the number of changes, but on an exponential basis. So in this formula, n, the number of changes, is significant. It's kind of important in terms of the way in which the total risk of releasing changes scales. So if we have a system like this, where we're going to be releasing large units of change once every 6 months or more, something like that, that's lots and lots of changes, then n is very large, and so the risk is high. Whereas if we have an approach like this, where we release incrementally in many small changes, then n is going to be relatively small. And so the risk is low. So incremental has this other benefit, as well as the modularity of our system. I want to show you a picture. I've stolen this picture from Jeff Patton's book, with a wonderful book on story mapping, because it's the best description to describe the difference between two very similar sounding words in English, iterative and incremental. So an iterative approach is like this. We're going to do a kind of rough sketch of the whole thing, and then we're going to refine that sketch over time until it's a beautiful, finished, complete version of the whole thing. Incremental is different. Incremental is more like this. We're going to do a little piece of the thing, and we're going to build it up sort of in a modular fashion over time. I think that both of these things are fundamental to any engineering practice. We need a rough sketch of large bits of the system to be able to try out ideas and understand them. And we also need these incremental ability and modular ability to separate out our systems and focus development in different parts. We want to be experimental. An experiment is a procedure carried out to support, refute, or validate a hypothesis. Experiments provide insight into cause and effect by demonstrating what outcome occurs when a particular factor is manipulated. I would argue that if you look at human progress, it was kind of a flat line for 200,000 years, and then it starts to tick up about 200 or 300 years ago, the age of the Enlightenment. When we started scientific rationalism, it was the introduction of science and engineering style thinking that really made the difference between a relatively agrarian, simple society to the modern high-tech society that we have today. Whether you think that's a good thing or a bad thing is kind of different, but that's the case. And so being experimental is fundamentally important. And I'm going to tell you another little my nerd-based stories. So in 1961, John F. Kennedy, President of the United States, stood up in front of Congress and said, we're going to send a man to the moon and bring him back. And in those days, they were all men, at least the American astronauts were. And so at that point in history, where were they? Well, this was 2 weeks after the first American had gone into space. And the first American that went into space was a chap called Alan B. Shepard, an incredibly brave man. Basically, they sat him on top of an intercontinental ballistic missile in a tin can and fired him about 60 miles up, and he parachuted back down. That was it. He was at that point, the intercontinental ballistic missiles, a Redstone rocket, they were blowing up all of the time. So he was an incredibly brave man. And so Kennedy stands up 2 weeks after that and says, we're going to send people into the moon. And everybody in NASA went, because they had no idea how to do that. They had no clue. And Kennedy's just put a deadline. He's just said, we're going to do that, and we're going to do it by the end of the decade. So Kennedy set the goal. I was telling this story to somebody and said, is this the biggest, most expensive user story ever? And I think it is a candidate. It probably is. So he set this goal for what we're trying to achieve. And here are some pictures of all of the things that they didn't know how to do, which is basically all of the things that you have to do. So they hadn't got takeoff sorted. Their spaceships, their space rockets were still blowing up on the pad. They hadn't got multi-stage vehicles sorted. They hadn't launched one yet. I don't think the Russians had either at this point. They hadn't got the splashdown sorted. The mission after Alan B. Shepard's mission, the capsule sank. They hadn't sorted all that stuff out. Nobody had docked two spacecraft together yet. And that's essential if you want this kind of modular moon mission. They hadn't got spacesuits sorted where you could walk. Nobody had done a spacewalk yet. All of this stuff was to do. So where do you start? Where do you begin? One of the ways is that you hire smart people. This is Margaret Hamilton. She's the first person to use the term software engineering. She invented the term, and she was in charge of the mission to write the software for the lunar lander. And if it wasn't for her work, doing some remarkably insightful design work without any requirements, she just thought it was a good idea, the Apollo 11 lunar lander would have been aborted because the computer became overloaded, and it was her load shedding algorithms that allowed the computer to make progress and to actually allow the spacecraft to land. So that's one thing. But the other thing is that you start to think about the problem. So here's a picture of the Earth-Moon system, right? Wrong. This is a kid's storybook picture of the Earth-Moon system. Doesn't look like this. This is a picture to scale of the Earth-Moon system. At this point in human history, no human artifact had been more than 1 pixel away from the planet Earth. So, problem one. How do you get from here to here? Incredibly difficult problem. Where do you begin? Do you begin by creating a Gantt chart? Do you begin by thinking, oh, let's plan everything ahead. Let's plan what we're going to be doing on Tuesday, 1968, what Fred's going to be doing on that day? No, you don't. You don't know. Everything's going to change over that period of time. What you're going to do is that you're going to start trying stuff out. You're going to start experimenting. You can imagine the engineers in NASA getting together the day after Kennedy's made his talk and saying, what do we do now? I don't know. I know. Let's build a spaceship, put 3 astronauts in it, send them to the moon and see if they come back. Yeah, maybe not. That's probably not the best idea. Why don't we build a spaceship, send it to the moon and bring it back, but just be automated, and then at least we won't kill any astronauts, and maybe we've got a chance of keeping our funding until the end of the decade. Well, that's better, but it's still hellishly complicated. We haven't got a clue how to do any of that. How are we going to do that? I know. I've got a great idea. Why don't we build a spaceship and just send it to the moon and land it on the moon, not bring it back. That nearly halves the problem. Oh, that's a terrific idea. Why don't we do that? And that's where this came in. This was that mission. There's one more thought. What does landing on the moon mean? Doesn't actually have to survive the landing on the moon. So that's this mission. This is the Ranger program. This is spaceships as bullets to see if you could hit the moon. So how did that go? Well, the first launch, it blew up on the pad. The second launch blew up on the pad. If you've worked in large projects, the next bit will amuse you, because what do you do if you're now behind schedule? Let's press on. The original aim of these was just to get them into Earth orbit. We didn't make that, but let's move on and let's go for the moon. So they went for the moon with the third one. It got into Earth orbit. It did the deorbit burn. It shot off towards the moon, except it missed the moon completely. The fourth one, it got into Earth orbit. It did the deorbit burn. It worked, but all of the systems on the spaceship failed as it left Earth orbit. And so they were able to observe it from the ground, and they saw it hit the moon, but they didn't get any data, really. The fifth one missed again. The sixth one hit the moon, but the cameras failed. So now they've got some telemetry, but they've got no pictures. The seventh one was a success. The eighth one was a success. And the ninth one was a success. When you're faced with a world-class problem, you've got access to the brightest engineers on the planet if you want them. What do? You experiment. You try things out. You try and figure out how things work. You design small steps and you try them out. There were millions of other experiments in the NASA program, in the Apollo program, beyond this. This wasn't the only experiment. There would have been experiments on each component of these spaceships of different kinds. But that's the thinking. You don't think about, let's do it all in one big leap. You think about, how do we decompose this into small steps, small, safer steps that we can learn from? And that's what they did. Here's another experiment for you. Has anybody seen this before? So the idea here is to decide which is the larger orange blob. The orange blob on the right or the orange blob on the left. Hands up, everybody who thinks that the orange blob on the left-hand side is bigger. Nobody. Hands up, everybody who thinks that the orange blob on the right-hand side is bigger. A few people. The rest of you are lying, you have seen it before. They're both the same. And we can figure that out through an experiment. So here's my experiment. They're both the same. Here's another one of those kinds of things. You've seen this one before? Yeah. Hands up, everybody who thinks that the line on the left-hand side is longer. Hands up, everybody who thinks that the line on the right-hand side is longer. Hands up, everybody who thinks that they're both the same. You weren't paying attention. I've been talking about experimenting. You have to do the experiment. The line on the right-hand side is longer because I cheated. You have to do the experiment. You can't rely on your judgment. You have to measure. That's my point. We want to be empirical, based on concerned with or verifiable by observation or experience rather than just pure logic. Maths isn't enough. Maths is wonderful. I love maths. It's not enough. We've got to maybe do the maths and then see whether it fits reality, because often it doesn't. We've got to measure based on the real world. Being empirical is absolutely vital to any form of progress that we need to make. It's going to be evidence-based. It means that we can separate myths from reality. We can do research. We can measure things. We can observe what's going on. We can try science. We can try learning from what we observe in the world. One of the things that's kind of a bit slippery about this idea, and that scares some organizations, is that we can never be certain of success. Progress only comes when we risk failure. We learn not when our guesses don't match reality. That's when we learn most. When our experiments go wrong, that's when we learn most. At Amazon, they encourage experimentation and discovery. And they measure what happens with their experimental culture. If they find that half of their experiments are not failing, they up the rate of risk in their experiments, because it's the experiments that fail that teach you the most. That seems counterintuitive, but it's the truth. Production will always surprise us, and it should. That's how we learn, that's how we adapt. So we want to optimize to get into production frequently so that we can learn and adapt based on what we observe. All of our design choices, all of our coding efforts, everything that we think about, all of the documentation, all of our tests are only the best guess of what's going on at any given point. So they're our best theory of what's happening in reality. Science works like this. General relativity is the most profound theory that we have in science, and yet there are organizations all around the world trying to prove that it's wrong, because we know that it's wrong. It's just our best guess so far. So, fundamentals of an engineering discipline. Actually, I think continuous delivery as an engineering discipline is a good thought experiment too. So, is it iterative? Absolutely. It's based on working very quickly in very short iterative cycles. It employs feedback. We concretely look to establish feedback channels so that we can learn and adapt. It's incremental. We can build systems up in these modular units loosely coupled from one another and understand how they stand. It's experimental. It gives us a platform for trying out ideas and adapting as we learn. And it's empirical. We're going to be going to production as frequently as we can manage to learn from that. We're going to be measuring things using experiments. It gives us these short feedback cycles, test-driven development, automation, hypothesis-driven development, tests as a falsification mechanism, the feedback channels that we talked about earlier, all of these things. Fundamentally, though, it's grounded in this. We're going to make an observation in the real world. We're going to create a theory based on our observations. We're going to make a prediction based on our theory, and we're going to test the prediction in an experiment. That is the scientific method. That is humanity's strongest problem-solving technique, and it's the founding principle of any engineering discipline. It ought to be the founding principle of our engineering discipline. We've learnt over the years that if you want to create software, you're going to design, develop, test, and release, and we've known that these are a continua. These are not discrete stages. If you divide your development process up into these discrete stages, you're going to be inefficient. So we want to be doing all of these things all of the time. And we're going to do those iteratively. We're going to move very quickly through those and learn and adapt as we go. This gives us a wonderful platform for this more scientific engineering kind of discipline. We can do things like measure the cycle times, how fast we go from idea to software working software in the hands of users. We can apply the kind of scientific model to these. We can have theories, make predictions, and we can go out into the field and see whether users like our theories and predictions, and whether and we can react to what we learn. We can drop the things that were bad ideas and do more of the things that are good ideas. Or we can have theories and predictions, and we can test those. We can evaluate those in laboratory conditions, if you like, as part of an automated test strategy. I think this is quite a good description of what continuous delivery is, but it's also a good description of what an engineering discipline is. And remember, when we do this, we get these dramatic increases in productivity and quality. I sometimes get pushback on this. I say, yes, but the craftsmanship was a good thing. It brought in some good ideas. It's about skill and creativity, and those are important. It's about the freedom to innovate, and that's important too. And it talks about apprenticeship schemes and that kind of learning. All of those are true, and I think they're equally true for any engineering discipline. This is not an aspect of craftsmanship. This is just good practice. So this is just as true of an engineering culture. But what engineering does is it adds on top of those things. It adds repeatability. It means that we can do these things more predictably and more reliably. It provides guidance and structure when we're stuck. It improves the quality of our output. It amplifies our ability to do good work. It improves the efficiency overall of our process. And it gives us some guidance when we're stuck at those points when we don't know what to go for. Well, what do we do now? Well, what do we observe? What do we see? What's our theory? What's the impact that we'd like to have? What's an experiment? What's our hypothesis based on that theory? What's an experiment that we could carry out? Give us a way of moving forwards. So, I'm not talking about being like engineers. I think that we should be engineers. I think we should take control of what engineering is for our discipline and start applying that kind of thinking to our development processes. I hope you all have a wonderful day. It sounds like a fascinating exercise in discovery today. So I hope you have a wonderful time. Thank you for listening. That's my talk.